Okay, so today we are going to finish up electronegativity. Kind of broached the topic last time. We saw that quick video, or it wasn't quick, but we saw that video. And then we're going to talk about polarity, which is good because now that we've covered Lewis structures, we can just kind of blow through that. We've done it all in lab today. But in order to understand polarity of a molecule, which is what the final topic is, we have to know Lewis structure, then the shape. So all of that needs to be known before we can even discuss polarity of a molecule. So hopefully we get through that today. And I think if we end up early, we'll just end early because we have limited stuff to do and I don't want to rush it all in one day. So just to review, bond length, bond strength, bond order. Okay, single bonds are the weakest. They are bond order 1. They are the longest bonds too. So weaker bonds tend to be longer. Stronger bonds tend to be shorter. And that bond strength, you can represent that with an energy, a value, right? The stronger the bond, the larger the bond energy. Think of it as the amount of energy you need to put into it to break the bond. So don't forget, when you make a bond, it releases energy. So towards the end of last lecture, we were looking at this AVEE, average valence electron energy. And what that was combining the energy it takes to remove any of the valence electrons into an average number. So instead of just looking at the easiest to remove one, which is either for sodium, it would be the 3s electron. For phosphorus, it would be one of the 3p electrons, and that's it. So in phosphorus's case, we're going to look at an average of removing both the 3s or the 3p electrons. So that's all that was. And there is a trend with average valence electron energy values. Metals tended to be lower than approximately 1.6, 1.06. You don't have to remember these numbers. Just to understand what kind of information you can get from them. Non-metals tended to be all above 1.26, and semi-metals tended to be right in that middle region. Which kind of leads us to a new concept, which is a little bit different, but it's tied to average valence electron energy, and that is electronegativity. So it's got a very unique definition. It's the ability of an atom to attract electrons in a shared bond, so in shared electrons basically, in a covalent bond. And this is a property of any element on the periodic table. It's not something you could directly measure, so you can't use an instrument. There's no way to measure it directly. You have to calculate it from other values. One way is to calculate it from average valence electron energy, but there's other ways. And because there's many ways to calculate it, there's many different tables of electronegativities. Some of those other ones are bond energies. We looked at ionization energies, right? Ionization energies are how we calculated average valence electron energy. But there's many ways to kind of figure out what an electronegativity might be. The values for electronegativities are relative, meaning the fact that something might be electronegativity 4 doesn't mean anything specific. It only is relevant. It only means something when you compare it to another one. So fluorine is 4, oxygen is 3.5. The difference between them, comparing them, that's what matters. And so no units. There is no, so we didn't get them from a direct measurement. There's no units to them. So let's go straight into this connectivity. I think this is not too difficult. Let me remind myself what this is. I did it yesterday, but I can't remember which one it was. 1 second. Oh, okay. Let's just do it all together. So this is the connectivity that I just listed to. It's page 277 in case you want to follow along. So here's a table of electronegativities. This is not the standard one. So the standard one that you're going to see is the Pauling scale. and it doesn't have electronegativities for noble gases normally. Fluorine is going to be 4.0 exactly. So this is a different one. So don't worry, just use this one for any of the workbook activities you have to do, any homework. But for any of the Master in Chemistry homework, please use the electronegativity table that the textbook comes with, the Master in Chemistry stuff comes with, which is the one you'll see all over the internet, usually. So 6, describe the trend, left to right. You can see that the trend going left to right, the electronegativity increases. Since we got these from average valence electron energy, and we got average valence electron energy from ionization energy, the trends are the same, right? Ionization energy going left to right increases. Same with electronegativity. And going top to bottom, which is question 7, it decreases. Same as ionization energy, same as average valence electron energy. So, you will not have to know any of these numbers. You just need to know trends. Which side is higher, which side's lower, okay? So compare the trends to first ionization energy. Explain any observed relationship. I mean, I just gave it away. These have exactly the same trends as first ionization energy, okay? It is easy to ionize metals, especially the group 1 metals, and as you go left to right, it gets harder. It's easier to ionize down the groups because you're removing an electron from a shell that is further away from the nucleus. So ionization energy trends follow the electronegativity trends. They're the same trend. They work the same way. All right, so this shouldn't be a surprise, or shouldn't be something new that's going to be hard to remember because it's the same. And the relationship between the average valence electron energy that we looked at earlier and electronegativity is, if you multiply that by 1.8, you get approximately an electronegativity that works, that matches most tables people use. So you don't have to remember that either. Just understand that there is a direct relationship between them, okay? So the numbers here don't matter so much, just understanding the relationship. So, trends, we've covered this. They increase across a period and decrease down a group. And there is another chart. So this is the Pauling scale of electronegativity. The previous one had 4.1 something for fluorine. This one's different, but it's the same trend though. It goes up as you go left to right. It goes down as you go top to bottom. What I would want you to remember is not the numbers, but the trend. And one thing is where hydrogen fits in. So 2.1 for hydrogen, it doesn't really belong there. It kind of belongs here in terms of where it is. And it's good to remember where hydrogen is because, I mean, you can remember the rest of the periodic table by just looking at it. Say, oh, oxygen's higher than nitrogen, nitrogen's higher than carbon. Just remember where hydrogen lies in that. Hydrogen is between boron and carbon in terms of what its electronegativity is. So the number again doesn't matter, just its position in terms of like what the size is. Okay, so let's get to why we care about electronegativity, and that is to determine whether something is a polar or non-polar bond. So what that means is a bond can share electrons evenly between the two atoms, and so the electrons are perfectly balanced between the two. One side or the other is not going to have more electrons than the other. And if that's the case, you get a non-polar bond. So what you're looking at here is, first of all, down inside, this is a fluorine atom and a fluorine atom. There's the covalent bond between them. The two fluorines are exactly the same. And so in terms of which one is more attracted to those shared electrons, they're the same. Their electronegativities are exactly the same. They're strong, high, 4.0, but they're the same. So in a tug of war for those shared electrons, it's even. So this is nonpolar. Now the colors, what do the colors represent? This is a computer calculation of what's called the surface potential. So you use a computer to calculate where the electrons are most likely going to create kind of more electron density, I guess, kind of where the heavier parts are where we're most likely to find the electrons. And where it's red is high density, and where it's blue is going to be low density. So when you look at one of these, I don't want you to say, oh, it's really red here, so it's going to be polar. What you need to look at is if there's an imbalance. One side of the molecule is more red, one side is more blue. If there's an imbalance, then it's going to be polar. One side is going to be positive, one side is going to be more negative. But here, there's no imbalance. It's pretty evenly spread out. So this is a nonpolar molecule. So a polar bond is the opposite. The electrons are unevenly shared. And a simple case is HCl. So hydrogen and chlorine, they have different electronegativities. So if you don't need to know the numbers, but you can remember that hydrogen is just to the left of carbon. It's far away from fluorine. Chlorine is right next to fluorine, so chlorine probably has a higher electronegativity. Chlorine attracts those shared electrons more than hydrogen does, and so those shared electrons are not evenly shared. They tend to hang around the chlorine more often. And that's why there is a reddish tint to this calculated surface here, because the electrons tend to hang around that side of the molecule more often. That side will then develop a partially negative charge as a result. The opposite side, where there is a lack of electron density, will develop the opposite charge, a partial positive charge. And that's where the polar bond comes from. A polar bond, polar meaning there's two sides. There's a positive side and there's a negative side. So this bond is a polar covalent bond. Just to be clear, ionic bonds cannot be polar/nonpolar. Ionic bonds, by definition, are positive attracted to negative. It's just two charges attracted. Similar to how you can describe that attraction with Coulomb's law. This is different. This is shared electrons, but they're just shared unevenly. Okay. So to represent those partial charges, and so when I mean partial, I mean not a +1, not a -1, a fraction of a charge. And we're being vague about what that fraction is, because it could be a large fraction, it could be a really tiny fraction. The generic way to represent partial in chemistry is to use a lowercase delta. So that's the Greek letter delta. You might be familiar with the capital letter delta. That's the capital triangle delta. This is a lowercase delta. Kind of like that. I don't know, however you want to draw it. But that means partial. So partial negative, partial positive. You're going to label, if you need to show that on a diagram somewhere, that's how you'd show it. You'd show the bromine sign is partially negative, the hydrogen side is partially positive. Okay. So, if we take a look at a couple different molecules, I can ask you, and here is the formula, HF, and this is how it's drawn up here. This is the calculated potential surface. What is the partial charge on hydrogen in HF? Is it going to be a negative partial charge, no charge, or a partial positive charge? That's a clicker question. So there's two ways you can answer this. I mean, not two ways, two pathways to get the right answer. So, people are saying, oh, my thing turned off. People are saying C for the most part, and you'd be correct in that case. So, there's two ways to kind of solve this. One is to just look at this potential surface, and it's showing very red on the fluorine side, very blue on the hydrogen side. Blue in these diagrams represents more positive potential. Red means more negative, and there is a negative side and a blue side to this molecule. So the hydrogen is getting a partial positive side, partial positive charge. Another way to solve this is just looking at the electronegativities. So fluorine is the most electronegative element on the periodic table. Hydrogen is not as electronegative, it's lower. So the partial negative is going to go with the most electronegative element. So fluorine gets the partial negative, hydrogen gets the partial positive. Okay? Oop. So here's another one, H2. What's the charge on one of the hydrogens? It looks like a sphere, but there's two H's in there. It's kind of not very elongated. All right. So this is, oh, this keeps turning off. This one is a little easier, but in this case, there is no charge on these hydrogens. Why? There we go. So first, some of you I think probably saw green was closer to electropositive, and you're like, well, if it's closer to the positive side, let's call it positive. But again, when you see one of these diagrams, these potential surfaces, there has to be an imbalance. If one side is more green and the other side is more orange, then yeah, one side is positive, one side is negative. But I don't see that. I just see green over wall. So it's kind of the same charge all over. And so there is no polar bond here. There's no one side's positive, one side's negative. Both sides have no charge at all. Another way to think about that is hydrogen's electronegativity. You don't even have to know it, but if you look it up, it's 2.1. What's the difference between two hydrogens' electronegativities? None. They're the same. So it's an equal tug of war. Neither one is going to gain more electrons than the other. So zero charge. Now, last one. This is called lithium hydride. Notice the position of the hydrogen. What is the charge on the hydrogen in this case? Takes a few seconds to kind of comprehend what you're seeing. So, click it over. Most of you, well, everyone has voted for A, and you'd be correct. So, in this case, there's lithium, there's hydrogen somewhere in that big blob. The negative potential is on the hydrogen side, the partial positive potential is on the lithium side. That should make sense to us. If you look at the periodic table, look at electronegativities. Lithium is all the way to the left. It is the least electronegative, or not the least, but one of the least. Hydrogen is more electronegative, so the negative is going to hang around the hydrogen. The electrons in this shared bond between them is going to hang around the hydrogen more often. So this is a neat case because you're seeing the same element take three different types of charges. Hydrogen in this case. Either a partial positive, zero, or partial negative charge, depending on what it's paired with. Alright, so you got to really look at the whole bond. You have to look at both atoms to understand where the polarity is. If the bond is polar, and which side has the partial negative, which side has the partial positive. Okay. Keeps shutting off. So we can look at a series of molecules that have some things in common like this. So these are all hydrogen with a halogen. And notice fluorine's got very red, very blue side to it. So there's a very strong partial positive, partial negative charge. But as you switch fluorine out to a bigger halogen, notice that I can't really see that there's a definite reddish side and a definite bluish side anymore. That's kind of gone away. I would almost call this nonpolar. You can still kind of see it here. This side's more red. You can see a hint of blue. This is starting to disappear. I can't see it. So how does that relate to what the differences in electronegativity are? Well, hydrogen versus fluorine. I looked up the electronegativities. Fluorine's 4, hydrogen's 2.1. If I subtract those two, I get 1.9. If I do the same thing for H and Cl, I get this. If I go all the way to Hi, the difference in electronegativity between these two atoms is small, 0.4. So you're going from a very polar bond because of the high difference in electronegativity to a very nonpolar bond because there's a very low difference in electronegativity. This is what confuses or frustrates people is what is the cutoff? Where is, what number, what difference in electronegativity can I start calling a bond nonpolar? And I would say there's not really a good cutoff, but around 0.4, some of those, that's approximately where you can start calling things nonpolar versus polar, okay? So we'll see examples with carbon and hydrogen. So for instance, this molecule here is butane. This is the stuff you burn in lighters. But there's just a bunch of carbon-hydrogen bonds in here. So this particular bond here, even though the difference in electronegativity, carbon is 2.5, hydrogen is 2.1, the difference is 0.4, just like that one. So even though there's a small difference, we, as chemists, we consider a carbon-hydrogen bond nonpolar. And so this is filled with nonpolar bonds. And that kind of influences how we expect this thing to behave. So what result does this have? Well, this doesn't mix with water. Water is very polar. It doesn't, polar and nonpolar things don't mix. This can mix with things like gasoline instead, which is also nonpolar. So anyway, there's that. Let's see what else is next. So, difference in the pull between, so as the difference in electronegativity between the atoms decreases, there's less of a tug to one side over the other, then the electrons start to get concentrated more towards the middle. So here they're kind of all in one side, and now you can see where the electrons are kind of shifting more back to the middle, where they're shared equally. Okay. So here is, I would put a big asterisk on this whole slide, but let's talk about this slide first. So technically, anything that has a difference in electronegativity is polar, but again, only by technicality. I would say closer to around 0.4 is where the cutoff is. But again, it's not a firm number. Like you could argue lots of differences. There's a lot of gray area there. But let's call it about 0.4 is where the cutoff is, where you could start saying below 0.4 it's nonpolar. But what happens if you match up two atoms that are greater than 2 electronegativity? So an example might be, let me see. Well, let me go back a little bit. Here we go. Let's match up potassium with fluorine, K and F. So you might be thinking, how am I drawing a covalent bond between potassium and fluorine? Well, that's incorrect to do, because if I look at the electronegativities, 0.8 and 4.0, what is the difference between them? The difference between them is 3.2. So that's the difference in electronegativity. That is a huge difference. It's a huge, huge difference. So if we apply what we know so far, if I were to try to make a covalent bond between potassium and fluorine, where I share electrons, what this is telling me is that fluorine attracts those shared electrons so much that the electrons hang around the fluorine almost 100% of the time. What I'm describing right now is an ionic bond. If the electrons are only hanging around the fluorine, then the fluorine has stolen the electrons, right? So potassium had its 1 valence electron, fluorine had 7 valence electrons. They're not going to share. The difference in electronegativity is too high. So instead of sharing, the potassium has given up its electron. The potassium is now going to have a positive charge. The fluorine now has a negative charge. And I'm describing an ionic bond. You have an attraction between a cation and an anion. So the idea here is when the difference in electronegativity is so high that it's above 2, you can't even make a covalent bond. The fluorine just rips the electron away from the potassium, and you make F minus and K plus, and that's it. They exist as ions. They're attracted to each other because of the charge, but they are free to go around wherever they want. If you dissolve this in a solution, for instance, So there's a sweet spot where the electronegativity difference is big but not big enough, and you get a nice polar covalent bond. So this really only happens, this area here, with nonmetals. All right, the metals electronegativity is so low that if you pair up a metal with a nonmetal, they don't share. They just, the nonmetal steals the electrons away. That's it. So we're kind of starting to leave our black and white thinking in terms of bonding and starting to kind of see there's a gray area here. So we go from covalent nonpolar to covalent polar, and then to ionic. In 222, we're gonna shatter the barriers even more. We're gonna throw in metallic bonding, and there's like this spectrum of bonding we're gonna look at. But anyway, for now, this is what we'll stick with. So non-polar covalent bonds, there's plenty of examples. If the two atoms are exactly the same, then that's a pretty obvious example. H2, F2. But if the electron negativities are really similar or the same, that's another example of a non-polar covalent bond. So C and S, carbon and sulfur, have the same, it's not listed, have the same electronegativity. Carbon's 2.5, sulfur I think is 2.5. If you look it up, it will be the same. Nitrogen is 3, chlorine is 3. So they are nonpolar, the bonds between those two atoms. And there's plenty of examples of polar covalent bonds. So HF, OCl, CCl, things like that. So as soon as you substitute one of those atoms for a metal, the difference in electronegativity is going to be so large that there's no longer any sharing even. It's just one electron is transferred to the other, and you end up with an ionic bond. Okay? Here's another view, kind of the spectrum of bonding here. So nonpolar to kind of polar covalent, very polar covalent, ionic. One way we can describe this, and in kind of the spectrum terms, is as you go to increasing electronegativity, you get increasing ionic character. So your bond becomes more ionic-like. And then as you decrease the electronegativity difference, your bonds become more covalent. They have increasing covalent character. So these are all descriptive terms we can use to describe the bonds now. So we can still use our black and white description, hey, this is covalent, this is ionic, things like that. But we can also use this spectrum description where you could say, oh, it's, and I'm going to throw a number in here, 50% covalent, 50% ionic. That's possible to do in chemistry, okay? HF is probably a great example of being really ionic and covalent at the same time. So I won't show you HF, but I'll give you an example of why there's a spectrum of bonding here. HCl in gas phase is considered very covalent. They share electrons. So this is all right, and let me do the Lewis structure properly. Here we go. But as soon as I dissolve this in liquid, I make hydrochloric acid. And suddenly in a liquid, it's ionic. It splits into H plus and Cl minus. So this thing is kind of both covalent and ionic at the same time. By itself, I would call it covalent. But like I said, it exists on a spectrum. There is some ionic character to it too. Okay? So we're going to make this more complicated as we go along. Not too much for this term, but next term it'll get a little bit more complicated. All right. But let's just do black and white thinking. Let's just, peg it on the board. Where does it belong? If I look at a CO bond, would I call it ionic? Any there? Polar ionic, non-polar covalent, polar covalent? Or is there not enough information? These are electronegativities right here. Okay, so people are saying C or D, so nonpolar versus polar covalent. So in this case, I would definitely say it's polar covalent, and the reason I would do that is I instantly try to calculate a difference in electronegativity. So carbon is 2.5, oxygen is 3.5. Doesn't matter which way you do it. The difference is 1.0. On the spectrum, that's right around there. So remember, this is non-polar covalent. This is polar covalent. And anything here is ionic. So this is a definitely polar covalent bond. It's smack in the middle of this giant region here. Okay. So which one is most polar out of these bonds? You don't have to calculate all of them. You can kind of eliminate some of them, but go. So, a little bit all over the place, but most people are voting A. And you'd be right if you voted A. So, when I meant you can eliminate some of them off the bat, you need to remember that the largest difference in electronegativity are going to be between elements that are close to fluorine versus elements that are furthest away. So look at how distant they are. The ones that are most distant will probably have the greatest electronegativity and therefore be most polar. So C is here, O is here. You can quickly calculate as 1.0. Nitrogen versus oxygen, they're closer together. It's going to be less polar. Nitrogen to hydrogen, that would you calculate 0.9, not as high as CO. Carbon to nitrogen, they're close together. Carbon to hydrogen, remember hydrogen sticks right about there. They're close together. So CO is the only one. CO is the highest difference in electronegativity, so it's going to be the most polar. So these partial charges that I implied that we don't care about the numbers. Well, what if we did calculate, measure them? What would they be? So here are two different compounds, HF and HBr. And the partial charges on each of them, notice they're tiny, 0.09, 0.09. But they're opposite. right? So one is a positive 0.09, the other is a negative 0.09. HFs are higher, but they're still not close to 1. If they were a full 1 or minus 1, then it'd be ionic. So partial charges, you can have those partial charges in covalent compounds, but once you get these full charges, you're looking at ionic compounds at that point. Notice that these are bigger. Why are they bigger than these? Well, look at the difference in electronegativity. HF is going to have a bigger difference in electronegativity, so it's going to make a more polar bond than HBr. And that's reflected in the size of the partial charges. So there's a very big imbalance of electron density in HF. The electrons are hanging around the fluorine more, because it's more negative on the fluorine. And yes, they're hanging around the bromine a little bit more than the hydrogen in HBr, but not as much as on fluorine. Not as negative. So all of the partial charges should be 0 to add them up for a neutral molecule. All right, now we'll throw in this this arrow to complicate things. So the arrow that you see on the screen is what is known as a dipole moment, or it's an indicator of the dipole moment. So a dipole moment is a measure of the dipole. Like a dipole is something that has two poles. It has a positive side and a negative side, or in the case of a magnet, a north side, south side, something like that. So we can measure the strength of the dipole. And if anybody's taken any linear algebra, vector calculus, anything like that, that's a vector. If you haven't taken anything, don't worry about it. The length of the vector corresponds to how strong the dipole moment is. But since it's a vector, the direction matters too. All right, so if you haven't taken any of this math, don't worry. Ultimately, what this arrow is showing is exactly the same thing these partial charges are showing. The arrow always points towards the negative side of the molecule, and the tail is always going to be towards the positive side. There's a little plus sign on the tail to remind us that that's the positive side. The length of the arrow, and we're not going to worry about it too much, but technically the length of the arrow indicates the strength of the dipole moment. So the bigger, the more polar the bond is, the bigger the arrow is going to be, or the longer it's going to be. So that's a dipole moment. And this is something we can actually measure. So let's see if we can see on the next slide. Oh, well, it's not here yet. But yeah, negative side, the arrow points to the negative side, positive side points to the tail is on the positive side. So dipole moment. If you want, this is something we can measure, and in an equation, you use this variable mu to represent it usually. So if you ever see mu, that's usually dipole moment. And it's the measurement of that polarity of a bond. So we use, where is it? There it is. We use this weird unit called the debye to measure the dipole moment. And so there it is, d. It's a debye. We're not going to see it much except for next week in lab. We're going to calculate these from a computer simulation. And so the larger this number is, the stronger the dipole moment. The larger the dipole moment, or the stronger the dipole moment, the more polar the bond is. So something like ClCl, two Cl's bonded together will have 0 dipole moment. HF will have a much bigger dipole moment than HCl. So this is HCl's dipole moment, and HF will be a bigger number. HBr will be a smaller number, because it's less polar. Okay, so just making sure that we can do this. If you have bonds like OH, you need to be able to look at this bond and say immediately which side is taking the partial negative, which side takes the partial positive, and then be able to draw a dipole moment for it as well. So how would I do that? Well, oxygen is more electronegative than hydrogen. You can look up the actual numbers. Oxygen's 3.5, hydrogen's 2.1. So this is going to have the partial negative charge. So I'd write a little lowercase delta with a minus sign. This is going to take the partial positive charge. And if I were going to represent or show a dipole moment, I would draw an arrow pointing in this direction with a tail starting at the hydrogen side. All right, so this arrow should be parallel to the dipole, like the direction of the bond. HS is a very similar kind of bond. S has got a much lower electronegativity than oxygen does. So even though S, sulfur, is more electronegative than hydrogen, you can look them up. I think S is 2.5. Hydrogen's 2.1. This is one of those, you could almost call it nonpolar, but let's call it polar in this case. But what I would know here in this case is the dipole moment would be a lot smaller. So the length of this arrow should be shorter than this one. How long it is, it's relative. It's up to you, but it should be shorter because the polarity of this bond is it's not as polar as this bond is. The difference in electronegativity between hydrogen and sulfur is smaller than the difference in electronegativity between oxygen and hydrogen. All right, so you can go through a lot of these. I don't know, maybe HS we should classify it as nonpolar. Let's call it weakly polar / nonpolar. This is where one of those gray areas. It's hard to judge. CI though. So carbon and iodine, and I need to look these up because I don't know what iodine is. Here's the table. Iodine is 2.5. Carbon is 2.5. Exactly the same electronegativity. This is pretty clear. The CI bond is nonpolar. So there is no dipole moment we can draw. There is no partial charges. So nothing. It's a completely even bond because they have exactly the same electronegativity. So that's what you'll have to do. Now this seems pretty boring, maybe? There's a reason we have to look at the bonds first. Oh, geez. Okay. Well, let's just. Here, I'll ask this one. Which one of these has a dipole moment? So, everybody keeps changing. There's no E. That's okay. None of the above, maybe? All right. So most people say C. The answer is C. CCl, 2.5 versus 3.0. The difference is not big, but it is 0.5, slightly higher than what our cutoff is. So that's technically polar. It's not very strongly polar, but it's polar. The rest of these, I believe, are like identical. Fe and Ni. The same. C and S are the same. F and F are the same by default. Okay. So, what do you think the dipole moment of HI is going to be if HCl is 1.11 to by? Make an educated guess on this one. Okay. So, most people voted D. if you did vote D, you were correct. So HI, I is down there, and I don't want to, I guess I can't bring it up anymore. I's electronegativity is 2.5. So 2.5. H is 2.1. The difference is pretty small, 0.4. So the dipole moment is proportional to the difference in electronegativity. So this is a much smaller difference in electronegativity than HCl is. So we'd expect a smaller dipole moment. So instead of being higher, it should be smaller, 0.45. It's not going to be 0 exactly, because there is a difference. We could call this a non-polar bond because it's so small, but it still has a measurable dipole moment. It's small enough that it might not matter for most bonds, though. All right. So I'm going to kind of rehash a little bit of what we're going over in the lab. We're going to come back to the bonds and the polarity of the bonds in a second, because we want to switch to polarity of molecules. But let me make sure that the Lewis structures and shapes make sense. I'm not going to do much of that because we went over it already. But you know, in order to do anything that we're going to do next, you have to first know how to calculate a Lewis structure. So make sure you know how to do a Lewis structure. Once you know the Lewis structure, then and only then can you figure out the shape of the molecule. All right, and knowing the shape of the molecule is going to be critical to getting what is known as the polarity of the molecule itself. So let's see, it keeps turning off. All right, so we'll get the polarity of the molecule last. So just to make sure, here are the steps that I think I went over even in lab. These are the same ones I use. You count total valence electrons, you draw a skeletal structure with a bond each, least electronegative element in the center. Do the octet rule for the terminal atoms, same as the outer atoms. If not all electrons are used up, add electrons to the central atoms. It's kind of a different way of stating what I'm saying is do the octet rule for the central atom. Then compare, this is a check. This is you checking your work. Make sure you're showing all the correct numbers of electrons and that they match your original total. And if you do the same, you're done. This is a different technique. I'm not a fan of this one, but this one works for some people. So for this one, instead of doing the octet rule for the central atom, using the electrons you have available, we're automatically adding electrons to the central atom and then checking to see if no, I don't like this one. Let's skip this. I don't like this. I should have removed this part of the slide. Sorry. But let's look at exceptions, because we didn't see all of the exceptions in lab. So obviously hydrogen takes 2 electrons, not 8. Helium does too, although we're not going to really see any bonds with helium. It's almost impossible to make a bond with helium. But helium will have 2 electrons in its outer shell. That's it. It's only got an S subshell. But beryllium can have less than an octet. So beryllium is a metal, and while we can normally we think of beryllium as a metal making ionic bonds, you can make weird covalent bonds with beryllium too. But in beryllium's case, and in borons, they do not have to have a full octet. It's one of the weird examples where you can break the octet rule. So for instance, there'll be more of this later. So, period 3 or higher nonmetals can have expanded octets. So you can break the octet rule if needed to add more electrons, and those electrons will fit into empty d orbitals. So we've done all this. Okay. This is just checking your work. Yep, we've done all this. So then we get to the shapes. So once you know the Lewis structure, you can determine the shape, and this is just as critical. We're only going to focus on these shapes for the final. You don't have to worry about these bottom shapes for the final at all. There we go. So honestly, you're going to have to memorize the names. So memorize these names. Make sure you understand how many groups of electrons give you this shape, things like that. Okay, so memorize the names. Kind of memorize the chart. I don't think you have to memorize the chart because it'll eventually come to you, get used to these shapes, you'll see them. But if you can't, yeah, you'll have to memorize it a little bit, okay? And you'll need to, at the very minimum, remember this tetrahedral shape. So learn how to use the wedges, the solid wedge and the dashed wedge. Please don't put a dot in any of your drawings. Replace that with whatever element it is. You won't need to use this for the final. So, let's do one more. Just example, just to make sure. For the people at home who can't see this and haven't seen the lab. So, let's do OCN. No, maybe not OCN. Yeah, OCN, why not? So, OCN, it's the clue into how it's ordered is right there in the way it's written. But remember, we're going to put the most electropositive, the least electronegative element in the center, which is the carbon in this case. So if I do a skeletal structure, it's going to look like that. And valence electrons. Carbon has 4, oxygen has 6, nitrogen has 5, and that negative charge, any negative charge adds an electron. Any positive charge removes an electron. So adding an electron, we have 16. And I've already drawn in 4 electrons. There's 2 electrons in each bond. So removing 4, I have 12 left. I'm going to satisfy the octet rule for the outer atoms first. 1, 2, 3, 4, 5, 6. Plus the 2 here makes 8. So I've drawn in 6. I've got 6 left. And I'll draw 2 here, or 6 here. Plus the 2 here gives me 8. And I've got none left. Now I'll do the octet rule for the central atom. And I don't have any more electrons, but this thing needs 4 more. It's only got 4 electrons next to it. So I got to share. And I know I showed you guys formal charge. But let's hold off on formal charge for a second. Let's just do it symmetrically. So what I'm going to do is I'm going to share a pair from this side, which will get me close. I have now 6 electrons next to the carbon. It's not enough. Well, let's share another pair from this side now. And then I end up with that. And that is a good Lewis structure, although I need to show that it is negatively charged. All right, next thing. I want to, and honestly, this is not the best Lewis structure, but let's just go with this for right now. Next, we're going to do electron geometry. So electron geometry, we look at the central atom. We count how many groups of electrons are on that central atom. So, wrong color. There is 1, 2 around that carbon. And if you look it up in the table, 2 groups of electrons means it's a linear electron geometry. Geometry. That's the electron geometry. That is the geometry the electrons force the central atom to, take with the electrons around it. Then you have to look at the molecular geometry. So now that we don't ignore the electrons, but we don't see electrons. We're going to see the atoms attached. In this case, there are atoms on both sides, and so the molecular geometry is also going to be linear. So linear molecular geometry. There you go. What are the bond angles? So there's no perspective drawing, it's just linear. So what are the bond angles? Well, it's linear, so it's 180 degrees for the bond angle, half of the circle. So that's what you should be able to do at this point, or at least close to this. I don't want to belabor this because we just did this in the lab. We'll see more examples when we do the polarity stuff. So let's move on, and let's get to the more advanced topics. So one thing we ignored was something called a resonance structure. And you get resonance structures when you start drawing molecules, and you realize you can draw them a couple different ways. So a lot of you did nitrate or nitrite, or you did sulfate or phosphate. And the thing was, well, where do I put the double bond? This oxygen or this oxygen? That's a perfect case where you have a resonance structure. So what does that mean? So if you can draw more than one valid Lewis structure by changing the placement of the electrons, not the nuclei, you're just moving electrons, then they are resonance structures. So this is where we get to formal charges. Formal charges is a way to figure out whether a resonance structure that you've drawn is the correct one or the more appropriate one or not. So they're not charges, electrical charges. These are just kind of tools we use to kind of visualize what's the most likely arrangement of electrons. That's it. So I guess a better way to think of formal charge is if all of the bonding electrons are shared equally, that's what the charge of an atom would be. But I'm not a big fan of the definition. I like to think of formal charge as the tool that we use to kind of understand the structure. That's it. So we covered the calculation for it in the lab. And it is, like the bottom one better, the number of valence electrons, so the original valence electrons for that particular atom you're looking at, minus the number of non-bonding electrons, lone pair electrons, on that atom, minus half of the bonding electrons going to that atom. So you have to calculate a formal charge for every atom in your Lewis structure. So, in a neutral molecule, the formal charges, if you do them right, all the formal charges should add up to 0. But if you have a charged ion, so like nitrate, then all of your formal charges will add up to whatever the charge of that ion is. Okay? So that's a nice way to check to make sure you did everything right. So here are two examples. This is one way to do carbon dioxide on the left, and another way is on the right. So instead of being symmetric, let's just share all the electrons from one oxygen and leave the other one alone. So these are both resonance structures. They're both possible ways to arrange electrons. We're not changing the position of any atoms, just the electrons. But is there one that's more correct than the other? I wish it would pop that up. But let's do that real quick. So let's do the one on the right first. This thing sucks. There we go. Triple bond. Single bond. So if we do the formal charge on this oxygen first, 6 valence electrons for the oxygen that's number 6, group 6. It's got 2 lone pair electrons, or 2 non-bonding electrons, however you want to call them. And then it's got 3 bonds, so 6 bonding electrons. So half of that is 3. So 6 minus 2 is 4, minus 3 is a plus 1. So there is a plus formal charge on this oxygen. If I do this carbon next, 4 valence electrons for carbon, group 4. There are 0 lone pair electrons, and half of the bonding electrons. There's 8 electrons in bonds. All right, 0. Fine. let's do the last oxygen. So 6 valence electrons, 6 lone pair electrons. There's 3 lone pairs, so 6 electrons, minus half the bonding electrons. 6 minus 6 is 0, minus 1 is minus 1. So there you go, there's that Lewis structure. If I were then to do CO2, I'm going to warn you in advance. A carbon with 4 bonds and no lone pairs is going to be 0 formal charge. It's the same calculation. So that's 0. And these 2 oxygens, they're the same kind of oxygen. So I'll do it once. 6 minus 4 lone pairs, or 4 lone pair electrons, minus, not 2, sorry, minus half of the bonding electrons. There's 4 bonding electrons. That adds up to 0. So everything is 0 formal charge here. And as we went in lab, if you compare 2 structures, the fewer formal charges are better. So having no formal charges is better than having some. If that's not, if every structure has formal charges in it, you want the ones with the smallest formal charges. That's pretty small, but 0 is better. And then beyond that, we want to put negative formal charges on the most electronegative element. Well, I don't have a choice. It's either this side or this side. It doesn't matter. They're both oxygen. So we'll see the other examples in a little bit. But this is the correct Lewis structure. This one is less stable because you got all these formal charges everywhere. So they are resonant structures, but this structure is a better one. It's the most likely to form. So again, quantum mechanics, we don't know exactly where the electrons are with precision, but we can say in probability wise, this is the most likely way we're going to see the electrons arranged. Okay? So formal charge. What's the formal charge on N1? Valence minus lone pair electrons minus half bonding electrons. Tired. Sorry. We got some people guessing. If you haven't guessed, it's okay. So, a little bit over, but oh, there we go. Change to C. It's 0, and it is. Nitrogen's 5 valence electrons minus the 2 that are already there, 3, minus half the bonding electrons, 2, 4, 6. Half of that is 3, 0. So that's good. And this is where my little thing on the board comes in. When normally you'll see, and I'll turn this on for the next one, this is nitrogen 2. Normally carbon has 4 bonds, nitrogen 3, oxygen 2, halogens 1. If it's not that, then it happens, but it's not the standard formal charge. So look at this one. 4 bonds in nitrogen, it's not standard. So it's not going to be 0. I'll give you that right now. So, everybody voted D. Yes, you're right. If you've taken any biochem, anything to do with amino acids, things like that, you'll often see this kind of nitrogen in amino acids and stuff. Just the way they draw them. All right. So, yeah, here it is, the rules. Atoms have formal charges close to 0. The negative formal charges should be on the atoms with greatest electronegativity. And I guess this is another way to state them than the way I did, but it works. So, OCN, the one I did over there, is that the correct way to do it? So, not really, because if I were to calculate formal charges on this thing that I drew, that's good. That's good. I'll spoil it right now. This carbon's got a 0. This oxygen is just like the oxygen in carbon dioxide, so that's 0 too. This nitrogen, though, is 5 valence electrons minus 4 lone pair electrons minus half the number of bonding electrons, which is 4. So 5 minus 4 is 1, minus another 2 is a negative 1. So there's a negative 1 on this nitrogen. What if I changed this structure a little bit? What if I, instead of making it symmetrical, I made all of the electrons come from the nitrogen side? So go back to this, the original thing, and I'm going to move this lone pair here and this one here. So I'll make this. Okay? So I didn't move any atoms, I just rearranged the electrons, that's it. And if I recalculate all the formal charges now, this nitrogen is 5 minus 2 minus half of, 6. There we go. So I get a 0 formal charge. 5 minus 2 minus 3 is 0. The oxygen now is 6 minus 6 minus half of 2. Negative 1. So the oxygen has a minus 1 now. And this should make sense, right? The formal charges of all of your atoms should add up to the overall charge on the molecule. So I get the negative in there. Which one's better? So negative formal charges are better off on the most electronegative element. Oxygen is more electronegative than nitrogen is. So this is a better structure because the negative formal charge is on the oxygen instead. So that is a better Lewis structure than the one earlier that I drew. Don't forget the bracket with the minus sign on it, but this one's better. But these are Lewis structures. And there's yet another one I could have drawn. What if I share all of the electrons from the oxygen side instead? If I did this. That's possible. So if I do that instead, I'm going to spoil it. I don't have to calculate it by hand. You'll end up with a positive formal charge here, and you'll end up with a negative 2 formal charge here. So it still adds up to minus 1. Plus 1 and a minus 2 adds up to minus 1. The charges work, but these are massive formal charges. Minus 2 sucks compared to just having a minus 1. So this is a resonant structure with all of these two. These are resonant structures, but they're not equal. This is the best one. This is the most likely to form in terms of how the electron is going to be arranged in that molecule. So notice, what can we say about the reactivity of this thing then? There's a strong bond here. The bond between carbon and oxygen is weaker. So if we were to do some kind of weird reactions, we could probably break this bond, maybe. So that's the kind of thing why we'd want to know this. Why we'd want to know which is the most common, most stable structure. So we can analyze it further and understand its reactivity and things like that. Okay, questions about that? So, oh, there you are. Which is close to the actual structure. It is, oh, this is a different one. Sorry, this is an even different one. So here's CNO. fulminating ion. Sorry, I was looking at it backwards. So notice the atoms are differently arranged than with the ones I was doing. And, well, I already gave it away, but these are all possible resonance structures, similar to the way I did mine. And to figure out which one's best, you can look at formal charges. So -3 plus and plus, -2 plus and 0, -1, 1, and -1. This is terrible. This is better. There's a 0 in there, but there's a -2 in the carbon. This might be the better one, even though there's a bunch of them. We have a minus on the oxygen. Yeah, we have a minus on the carbon. It's hard to say. This one's a lot harder to say. So, in reality, all of these are possible, and sometimes some are more likely than others. So maybe there's like a sharing between these two, like it's a kind of flip-flopping between these two, if it's hard to tell the difference. This is actually the more common one, but I would bet that if we looked at kind of how the reactivity works, you'd see this in combination with this. Like the true picture is a combination of them. And that's what makes resonance structures weird. So we'll get into that in a second. Here is, this is actually from the lab. Oh, and the dots are all messed up. So this is nitrous oxide. This is laughing gas from the dentist's office. It's also nitrous if you like racing. Same stuff you put in the car. What is the correct resonance structure? You can either have a triple bond between the nitrogen, double-double, or a triple bond between the oxygen and nitrogen only. I know the dots are messed up. But to know which one is which, you do the formal charge calculation and everything. And it's pretty clear that one's not it, because we have a large formal charge. But between these two, putting a negative on the oxygen versus putting a negative on the nitrogen, this one's better, negative on the oxygen. And that makes sense for how nitrous oxide works, at least in automobile racing, because there is a single bond between the oxygen and the nitrogen. You inject this into your engine. That bond is really easy to break, and you get this free oxygen atom to react with your gasoline, and that's what gives you all the boost of power. If it looked like that, it wouldn't make as much sense because there's a stronger bond to break. So you need a really easy bond to break, so you can provide all this free oxygen to your engine. Yeah.
So then, when it's reacting with our bodies in the dentist office, is it like giving more oxygen to our brain?
I have no idea the mechanism of what happens with lactic gas. My guess is that it's just, I don't know. I don't know what neurons it interferes with, because it makes you loopy. So it's I don't know. I have no idea. I'm sorry. You know?
Well, it causes euphoria, so maybe something to do with well, it's not dopamine. That's a bit too towards pleasure.
Yeah, it's beyond my knowledge skill set. It's doing something with your brain, that's for sure.
It's a different neurotransmitter.
All right. Oop, wrong one. So we're good with this, I think. What I want to get to next, let's see. Oh, I'm missing something. Before I get to this, we're going to go back. There are resonance structures that are not as cut and dry, put it this way. So, and we can't make you draw these because this is beyond your level at this point, but there is a very common molecule called benzene in organic chemistry, and I'm sure you've seen it. It's got the alternating double and single bonds, and it's a ring of carbons, 6 carbons with 1 hydrogen on each. That is kind of what the chemical structure of benzene is. In fact, it's actually much more commonly drawn like this. It's a hexagon, a line drawing, with a circle within it. Sometimes you've seen it like this, sometimes you see it as a hexagon with the actual double bonds like this. These are all the same thing. These are all benzene. But I want you to look at this double bond. Why is it here and not here between these two carbons? Why is this here and not here? Well, you could just as easily draw the version of benzene where I am not moving any atoms, I'm not rotating it, but I am just swapping the positions where the double bond electrons are. These are resonance structures. So these are resonance structures just like the ones we drew over there. The difference is there's no preferred structure here, right? If I do the formal charges and everything, it's all 0 here, it's all 0 here. There's no difference between them. So which one is the, like which one is the true picture? So if we had a way to label this carbon and this carbon, like somehow radioactively label it and say, oh, the double bond is between the radioactive carbons. Or maybe it's not between the radioactive carbons. How do we know which one's which? The true picture in chemistry is that it's a combination of both. So we're going to get to this more high-level concept, but these electrons that form the double bond, the second pair of electrons, are actually mobile. They can actually move around the ring. So sometimes they're between these sets of carbons, sometimes they're between the other sets of carbons. They're mobile. And so the actual bond order of each carbon-carbon bond is not 1, and it's not 2. It's on average 1.5. So that's where we get these fractional bond orders. This is a failing, actually, of Lewis structures. So Lewis structures are great. They're very powerful. They're organic chemists use them a lot. But it doesn't show this 1.5 bond. There's no way to show that. You have to just remember, oh, there's a resonance structure. It can look like this or like this. And that's why we draw benzene like this sometimes, where there's a circle inside rather than these double bonds. Because the circle represents these free-flowing electrons that can move around the ring. So resonance structures are more important than we're talking about right now, okay? So there's plenty of other resonance structures. If you did nitrate in your lab, nitrate looks like this. We'll come to this in a second. But that's nitrate, but why would you put the double bond here? Why not here? Why not here instead? And in fact, the double bond moves around in real life. So we'll come to that in a second, but let's get to the polar stuff before we run out of time. So now that we understand how to draw Lewis structures, and then we can take that Lewis structure and get a shape out of it, so we know the three-dimensional shape of the molecule. Is a molecule polar? So to answer that question, we need to know, does it contain polar bonds? And how do the polar bonds interact in that geometry, in the shape that it's in? So I'll start with the complicated way to think about it, which is you need a good way to visualize in your head three-dimensional stuff. So does the molecule have an uneven distribution of electrons, creating a dipole over the entire molecule? So like, is this bond and this bond and this bond all together creating an uneven distribution of electrons, or is it kind of balancing out? So if it is, if it's creating an uneven distribution of electrons, it's polar. If it's not, it's going to be nonpolar. So let's start with hopefully a simple one. So carbon dioxide. I think this is the easiest one to see. Carbon dioxide, let's do the Lewis structure. It has two polar bonds in it. But each polar bond is kind of opposing the other one. So what I mean by that is, here's CO2. If I look at each bond separately, so looking at this bond, that's a polar bond. Oxygen's more electronegative. So there's a partial negative on the oxygen and a partial positive on the carbon. If I draw the dipole moment, it's going this way. Okay? But now if I look at the next bond, this one here, well, same thing happens here, it's just going the other way. There's a partial negative on this oxygen, a partial positive on the carbon from that bond, and the dipole moment goes the other way. And it's exactly the same length, because it's exactly the same two atoms, the same bond as the other side. But notice what happens. These two dipole moments are pointing in exactly the opposite directions. In vector math, these would cancel out. They add up to 0. Think of it like a -1 and a +1 added together. They make 0. So overall, this is a non-polar molecule. Even though it contains polar bonds, it's non-polar because the bonds cancel each other out. Or the bond's polarity, I should say, cancels. Dipole moments cancel each other out. So you kind of have to think spatially, think three-dimensionally in your head in order to understand that. There we go. And there's the electrostatic potential. So again, don't look at the colors themselves, but look at the distribution. There's no one side that is more red than the other, or blue, or anything like that. It's kind of distributed evenly. So it's nonpolar, but is the best counter to this first one. Water is not linear. It's got 3 atoms just like carbon dioxide, but it's not linear. And because it's not linear, it's exactly the opposite. It's polar. So the way you should think about it is, here's your bent shape. And again, you need to know the shape in order to understand whether it's polar or not. So once you know it's bent, well, here's the dipole moment going for this bond, right? It goes from hydrogen to oxygen. Oxygen is more electronegative, so the arrow points that way. And then for this bond, the dipole moment goes that way. And they're not opposing each other directly. They're not going to like cancel each other out whether they're going this way or this way. They're combined pointing upwards. So if you like the math part, you can break it into x and y, and the x's part can cancel out, but the y's go that way. They overall point this way. And so the fact that there's an overall dipole moment means that this molecule is going to be polar now. So what I mean by that is, since the arrow is pointing upwards, this molecule overall has a partial negative charge on that side of the molecule, and on this side of the molecule is going to be a partial positive charge. All right, distinct from the bond partial charges, okay? This is, honestly, this I think is the hardest thing for people to visualize. Some people just can't visualize 3D in their head very well. But I have a solution to that if you give me a few minutes. So ammonia is a similar molecule. It's not flat, it's not linear. It's got this interesting shape called trigonal pyramid. And because of that, it's polar. The nitrogen is more electronegative than the hydrogens. And they don't like all cancel each other out. They kind of all point in this direction if you add up every single dipole moment. If it was flat, then they would kind of cancel each other out. But if it's not flat, they're kind of all pointed slightly upwards. So the dipole moments of each bond are pointing upwards overall. This is a polar molecule. So dichloromethane is one of my favorite examples because if you draw the Lewis structure and you just look at the Lewis structure, you might be fooled. So the Lewis structure of dichloromethane, one of them you could draw, would look like this. And if you just looked at the Lewis structure, you could be fooled into thinking, oh, this is nonpolar. Because there's a dipole, this is a polar bond, and that's a polar bond. And they're pointing in opposite directions, so they cancel each other out. But that's wrong. This is not a nonpolar molecule, because that's not the way it looks. It looks like this. It's three-dimensional. It's tetrahedral. The true picture of dichloromethane is something like this. Okay, and so now if we look at the dipole moments, you've got one going this way and one going this way. And I think it's pretty clear now that the dipole moment is overall in that direction. There's no canceling out like you can see with this. This is the wrong way to look at it. So this is a polar molecule. You can see it there too. Formaldehyde is a polar molecule. Alright, so one way to do this again is you look at every single bond in the molecule. Is it polar? If it's polar, draw the little dipole moment. You can ignore carbon-hydrogen bonds, right? They're close to being nonpolar, so we're going to call them nonpolar. But carbon-oxygen is polar. Carbon-chlorine is polar. And then you combine them together and you see if overall they cancel out or if they don't. So, here's some examples where you get nonpolar structures. So BF3, this is boron trifluoride. This is one of the exceptions to the octet rule. Boron likes to get fewer electrons sometimes. It's happy with just 6 around it. That's just how boron is. It's because it's one of those weird nonmetals, or semimetals, excuse me. But because of that, boron is trigonal planar. It's got 3 groups of electrons around it. It's flat. It literally looks like what you see in the screen. Every one of those bonds right there is very polar though. BF is a very polar bond. But this going this way, this one going this way, and this one going this way happen to just add up to 0. They cancel each other out. There is no one side of that molecule that is more negative than the other. So this is a nonpolar molecule despite containing very polar bonds. And there's the calculated thing. So yeah, it's very polar. The bonds are, I should say, are very polar because you've got this large amount of electron density on each of the fluorines. But I can't look at the overall molecule and say, hey, this side of the molecule is more negative, this side is more positive. No, it's negative all around. It's positive in the middle, but there's no side. Right? This is flat. It's not like the boron is pointing up and out. It's completely flat. This is a nonpolar molecule. It's weird how that works, but that's the way it works. Nonpolar. So you can change what's connected and suddenly make it nonpolar or polar. So CF4 is a tetrahedral molecule, just like this one was. But if all of the atoms attached to that carbon are all fluorines, then every single polar bond is the same, and they just add up to nothing. There's no side of that molecule that is more negative than the other. So that is nonpolar on the left. But if I replace one of the fluorines with a hydrogen, suddenly there is an imbalance. The hydrogen side is the positive side. This bottom side is the negative side. And it's polar. Okay. So, if you're like, I don't know how I'm going to figure this out, because I can't see this yet, I have some ways, shortcuts to figuring this out. So, one of the ways I've figured out that you can quickly tell if it's polar or nonpolar is look at the electron, find its molecular geometry. So if the molecular geometry matches, so if the molecular geometry matches the electron geometry, and 2, all the outer atoms have the same electronegativity, or just if they're the same atoms, they can be the same electronegativity too, then it's nonpolar. But if these 2 conditions are not satisfied, it is polar. That's the best I can do for you. So let's see how that works. This thing right here the electron geometry is tetrahedral. The molecular geometry is tetrahedral. So they match. And all of the outer atoms have the same electronegativity. So it's nonpolar. Over here, molecular geometry is tetrahedral, electron geometry is tetrahedral, but the outer atoms are not all the same electronegativity. So it is polar. If I go back a little bit, we can try this on other ones. Here, BF3. The electron geometry is trigonal planar. The molecular geometry is trigonal planar, trust me. It is. The outer atoms all have the same electronegativity, so it's nonpolar. And it is. This one right here is supposed to be polar. So yeah, this is trigonal planar electron geometry, and the molecular geometry is trigonal planar, but the outer atoms are not all the same electronegativity, so it's polar. So that's the best I can do. If you can't think three-dimensionally, remember that. You need both conditions satisfied to be nonpolar. Otherwise, it's going to be polar. Hopefully that helps. Okay. Let's see what else we got. So, I already gave that one away. So what about, well, we know this one already. Oh, jeez. So yeah, the second one. Well, actually, just shout it out. What do you think? The second one?
Polar.
Polar. The electron geometry is tetrahedral. There's a lone pair here, so 4 groups, tetrahedral. But the molecular geometry is trigonal pyramidal, so the shapes don't match. So it's polar by default. This one we already know. This one's water. Water is definitely polar. HF, that one's pretty obvious, hopefully. It's just one bond. So the molecule itself is polar. We already did this CO2. It's non-polar. What about this one?
Non-polar.
Yeah, non-polar. It's trigonal planar. It's flat. The molecular geometry is trigonal planar. Electron geometry is trigonal planar. And all the atoms are the same. All O's. Or all the outer atoms, I should say, are the same electronegativity. So it is non-polar. This is another one. Is this thing polar or non-polar? Guess you're gonna guess. Everybody says it's polar. Yes. So it is actually tetrahedral. Oop, I don't know why it's not showing it. It's tetrahedral. It's just like this one, where if you draw it the correct way, you'll see that the fluorines are going to be on one side, and so it's going to be polar. So I think that's it. Yeah. Ignore that. All right, we're done with today. We're not going to do much more of this stuff beyond today. So next week, we're going to tie in the shapes that we've learned to the orbitals. So how do the orbitals make those shapes? And it's going to get a little gnarly. So hopefully you're comfortable, or at least starting to get comfortable with Lewis structures. So you need to be able to do, quickly take a molecule, turn it into a Lewis structure, and then turn that Lewis structure into a shape, and then turn that shape into is it nonpolar or polar? This will be great quiz questions for next week. So make sure that you can do that at a reasonable speed. You don't have to be experts, but you need to be able to get through it. All right. This is pretty much all of OChem, by the way. So if you like thinking of molecules and shapes, and this is very much organic. So a lot of people struggle with organic because they're used to all the math that we did in Gen Chem and all the conceptual stuff. Organic switches gears, and you're just, it's like a lot of visual stuff. So you have to buy a model kit and everything. Yeah. But you can get through it. It's not too bad. Just takes a little training. Take it easy. Have a good weekend.